Good morning, ladies and gentlemen. Wait, should I say good evening perhaps? Welcome everybody to this presentation of our work titled On the Automation of Auditing in Power Grid Companies. This work has been authored by Sergio Chica Manjarez, Andrés Marín López, Daniel Díaz Sánchez, and Florina Almenares Mendoza. We're all researchers from the Department of Telematics at the Carlos III University of Madrid at the Ganés. So this work focuses on the security of power grid companies, specifically in the tasks of network and other equipment's auditing. Auditing is one of the common tasks required to secure networks. In power grid companies, the growing number of connected devices requires auditing approaches to scale. Besides this problem of scale, auditing should facilitate continuous security assessment to achieve continuous monitoring. Our understanding of this is twofold. On one hand, the necessity of establishing a link between the assets inventory of the companies and the auditing processes. On the other hand, auditing should follow an automatic or semi-automatic approach. Security assessment is defined as a circular process of assessing assets for their security requirements based on probable risks of attack, liability related to successful attacks, and costs for ameliorating the risks and liabilities, according to the standard developed for handling the security of power systems and associated information exchange, standard IEC TS 62351. This paper addresses an automated solution which may be part of an automated security control assessment, as described in NIST IR 8011 publications volume 3 and 4. The U.S. National Institute of Standards and Technology and the Department of Homeland Security are working in defining capabilities of automation support for ongoing security control assessments, such as software asset management and software vulnerability management. Software asset management is defined as part of the continuous diagnostic and mitigation process. Its main purpose is to control risks created by unmanaged or unauthorized software installed on a supervised network. The authorized software installed on every device is inventoried, and every software asset is usable and automated, being described in terms of Common Platform Enumeration Names. CPE is a standardized method of describing and identifying classes of application, operating systems, and hardware devices present among an enterprise's computing asset. Software asset management supports vulnerability, configuration settings, and hardware asset management. Software vulnerability management addresses defects present in software on the network. Once software and hardware are part of the inventory, software vulnerability management capability supervises software vulnerabilities in the company's software in order to manage and patch them in an appropriate manner. Software vulnerability management manages and assesses two kinds of software flows: the common weakness enumeration, which mainly come from poor coding practices, and the common vulnerabilities and exposure, which is a list of publicly disclosed vulnerabilities, those coming from working with software providers, vulnerability coordinators, bug bounty programs, and vulnerability researchers. Researchers, developers, and industry have developed tools for automating these capabilities. We have studied a number of them in this work, as you can see in the comparative table. In the table, only 4 of them show support for full automation. Linus, which is restricted to auditing of Linux, Mac OS, and other Unix-based systems. Crosono, which was an exotic approach to do the auditing of your wireless networks using a flying drone. Intric Core, which limits to vulnerability discovery but not performing the exploitation and post-exploitation pentesting phases. And finally, Leviathan, which notably uses mass scan, or offers the use of mass scan for conducting large-scale scans, and also uses some public service discovery like Shodan and Census to find vulnerabilities, and offer a number of exploitation for systems like shell shock or Windows double pulsar or eternal blue. We can see that none of the tools support all the analyzed characteristics. Cyber threat intelligence challenges organizations since none by itself has access to sufficient information for accurately addressing the threat landscape. Sharing cyber threat information among trusted partners and communities alleviates this situation, thus the importance of shared logs capability. Let's review the requirements of Auto-Auditor, the automated auditing system we propose for power grid companies. We have identified 8 requirements, so 4 in this slide and 4 in the next slide. So first of all is testing heterogeneous devices. The system we propose should be able to test a wide range of device types, from smart meters to networking elements and many other limited devices, and also laptops, normal computers and high-end computers. Second requirement is fingerprinting equipment under test, so fingerprinting devices. Due to the great variety of devices in the network, the system should be able to perform a semi-automatic fingerprint of the device that will be supervised by the company to achieve a highly accurate fingerprinting. So the idea is that such fingerprinting could be used to update the company inventory. Third is include known vulnerabilities under metadata. The system should fed itself with the potential vulnerabilities databases, such as open source databases like CVE, CV details, etc., and gather the vulnerability and severity information metadata. Fourth is to make the test plan configurable and to include executable and demonstrable attack vectors. That means that the system should select among the potential vulnerabilities only the set which have available exploitation modules. So at this point we are not doing the testing, okay? So we have already identified and now we want to do the testing. So all the selected modules will be included in a test plan and encapsulated in some format which allows manual editing and therefore including other modules, attack vectors and parameters. Requirement number 5 refers to the connection. The proposed system must include the capability of defining configurable connections, including different network parameters for running the different tests. Requirements number 6 and 7 refer to the link with the inventory system, so that the test plan can be manually or automatically executed, or even better, scheduled from the inventory system. That may require instantiating connection elements according to the defined connection configuration. The test execution output should be compatible with the inventory system. And finally, the number of required test execution may involve a large number of resources, but it must scale with the number of devices. Let's briefly review 3 aspects of the system design. We have chosen containers over virtual machines because they are lightweight and start-stop faster. Regarding the connection configuration assistance, we have identified 4 different scenarios. First, to provide physical access to the devices. Second, to provide an exact copy, the container or virtual machine of the device. Third, to set up a secure connection with external auditing system. And the last scenario is to execute the local auditing system in the company's network. Since the last scenario scales better, we have chosen it as a cornerstone in Auto-Auditor. Regarding vulnerabilities, we are using CVE scanner, the result of a previous work. The scanner performs a fingerprint of the device and outputs the vulnerability of the detected product and versions. We consider the CVE reference plus the severity according to CVSS 3x metrics. That metadata is incorporated in the database of vulnerabilities and linked to the inventory entries. So, how does it work? What is the workflow of AutoAuditor? Well, it starts gathering information with CVE scanner. It's imperative to conduct an initial scanning phase in order to gather all information of the environment needed for the attack plan. The data from the CVE scanner provides a fingerprint of the devices in the network to identify potential vulnerabilities. Right after identifying potential vulnerabilities, next step is to build the attack plan to exploit such vulnerability. An attack plan can be generated using AutoAuditor or manually created in the correct format. AutoAuditor allows execution of attacks through VPN if an open VPN configuration file is provided. The previous steps may be executed at an outsourced security company, but the remaining 2 steps must be executed at the power grid company. AutoAuditor will start a container with all the necessary tools to carry out the attack. If an open VPN configuration file is provided, another container with an open VPN client will start to serve pivot to execute the attack. After the attack execution, results are collected for introduction in the inventory system. So to test the correct behavior of the system, we have developed a closed environment including the devices, the VPN server, and the application performing the audit. Figure 1 presents the execution times of 2 different experiments. Blue dots represent different runs of the AutoAuditor with a test plan of 2 vulnerabilities. Red dots correspond to a test plan of 5 vulnerabilities. In the figure we can see a high number of outliers. This is mainly due to the nature of the exploits. Sometimes it takes a lot of tries to compromise the target. Sometimes only a few are required. First execution will take a high execution time due to the download and instantiation of the container images. To conclude this work, we have identified the requirements of power grid companies for an automatic auditing system, and we have designed and implemented the AutoAuditor. Thanks to the reviewers, we reckon we missed one requirement, which is adoption of the AutoAuditor by the industry and how to foster this adoption. So, besides our open source strategy, we plan to conduct a survey to check the acceptance. Finally, for future work, we plan to persist the auditing results in a blockchain for improved accountability of energy suppliers' critical infrastructure. Thank you very much.